Okay guys, so today we're going to talk about air pressure or atmospheric pressure. So before we do that, we're going to have to revisit some old concepts regarding how atoms and molecules behave under different temperatures. So as we know, if we assume that these two are the same volume, okay, the warmer side is going to have more molecular excitement. As a result, the atoms and molecules are going to be more spread out. The cooler atoms and molecules are going to be more lethargic and less excited. Okay, so if we assume that they're both the same volume, that means that there's less molecules in this one than there is in this one. Even though this one is more excited, that's the actual reason why there's less atoms per volume. It's more buoyant. Okay, so this is why warm air rises above cooler air, and why warmer liquid rises above cooler liquid, because it's less dense, it's more buoyant. Okay, as a result. In contrast, the cooler liquid and air always sinks relative to the opposing air mass or body of water. Okay, so warmer places have more molecular excitement, cooler places have less molecular excitement. More molecules per volume equals something called higher pressure. Okay, we know that also means higher density. Okay, so new concept, high and low pressure. So high pressure systems, okay, they're heavier. They have more atoms per volume. Okay, so cooler air, this is cooler air, okay, because like I said, the cooler air has more molecules per volume because the atoms are less excited. So as a result, the cooler air, the high pressure system is going to sink towards the earth. Okay, low pressure systems are always going to rise, okay, above the Earth's surface. Now, the universe wants to have equilibrium, okay, always. So, for this reason, the high pressure system that's now on the surface of the Earth is going to be sucked in to the low pressure system that's rising towards the sky, okay, because the surface of the Earth wants to be balanced, okay. The more molecules down here is going to travel to the less molecules over here, the one that's traveling towards the sky. So this is what causes wind. Okay, this is what causes a lot of the weather patterns that we're very familiar with. Okay, so when you watch the Weather Channel, you'll always see that they use various symbols that have different meanings, but one that you'll always see is the big blue H and the big red L. The big blue H is always going to indicate the presence of a high pressure system. Okay, the big red L is always going to indicate the presence of a low pressure system. Okay, so this is this is, like I said, what drives a lot of the weather that we know. So as I said on the back, the cooler air is associated with higher pressure. It's going to sink. Warmer air is associated with lower pressure. Okay, so it's going to go up. And these are all relative concepts. Okay, both of these air masses have the same volume, but the cooler one sinks. Okay, because of its higher pressure, the warmer one is going to rise up because of its lower pressure. Okay, more molecular excitement equals less atoms per volume. More buoyant, less pressure, less density. It's going to rise. Okay, now you'll notice that I got these funny looking arrows going around the H and the L. That's because if you have to imagine looking down at this from the sky. Okay, this is a two-dimensional picture, so you have to imagine looking down at the sky, and you'll see that these air masses, depending on their pressure, rotate either counterclockwise or clockwise. This is because of something called the Coriolis effect. This is because of the way the Earth rotates, okay, on its axis. It actually deflects the wind in different directions on the planet. Okay, so the Earth is constantly rotating, and forces are either driving the air up or down. Okay, but one thing that's for certain is that high pressure systems sink clockwise. Low pressure systems rise counterclockwise. Okay, so high pressure systems come down, low pressure systems go up, the high pressure system gets sucked into the lower pressure system, and that's what creates that wind. A really good way to see this firsthand is if you're standing on the shore or on the beach or by a big body of water. You'll notice that you'll really feel the wind. You're feeling the wind because the solid ground, the solid earth, gets warm faster than the sea. So that's going to create a relatively lower pressure on the shore. Okay, so that's going to drive up that air, and then that sea is going to fill that void. So that sea is going to rush into shore because of its opposing pressure system. Okay, so you're standing on the shore gets warm, low pressure, boom, that higher pressure, that relatively higher pressure coming from the sea is going to come and fill that void. It's going to fill it like a vacuum. Okay, so as you can see right here, I have the sun pointing towards the lower pressure system. It's lower pressure because it's warmer, counterclockwise towards the sky, high pressure clockwise towards the earth. It's going to fill that void, it's going to suck it in, and then that's what you're going to feel as that wind. Okay, so just to revisit, high pressure sinks, it's cooler, low pressure rises, and both of these air masses have the same volume, just they have just different density, different pressure. Okay, and this is all because this direction of these arrows is all because of the Coriolis effect, the way in which the Earth rotates, deflecting wind in different directions on the planet. And I want to add that if you were on the southern hemisphere, if you were below the equator, it would actually be the opposite right here. If you look at this diagram right here, you'll see the high pressure system is still going to fill the low pressure system, but the high pressure system is going to be spinning counterclockwise towards the earth. It's high pressure, it's always going to go towards the earth. And then the low pressure system is going to go up towards the sky clockwise. The roles will be reversed. Cool, guys. Air pressure.